Arden Labs, specializing in high-performance software consulting, training, staffing, and development. Module 13, Benchmarking. You are now watching Lesson 13.4, IO-bound benchmarking.
Let's now look at an IO-bound benchmark, an algorithm, and see what the dynamics are when we run the Go program single-threaded as opposed to that 8 or multi-threaded program. We already saw what happened with CPU-bound workloads. We proved that we need parallelism in order to get some better performance. We talked early in the class that when it comes to IO-bound workloads, that we don't need parallelism to see a performance improvement with concurrency. And let's see if we can prove that. So similar to our CPU-bound, we're gonna generate a list, a large list of documents. In this case, what we're gonna do is generate 1,000 documents to read. And that's what that generate list does on line 25. Now, I've created my own read function because I want to make sure that the latency is consistent across all of these two tests. So we're going to simulate an actual read by using line 34 and simulate that that disk read is taking a full millisecond. I think it's reasonable to say that any disk read would take at least a millisecond of time. So we're going to have a very, as consistent as it can be, kind of latency on that system call. And then we'll do a little unmarshalling there just to actually do some work. So that's our read call. So let's take a look at our sequential version of find there on line 42. You can see it's going to take that collection of 1,000 documents. And just like the add function, we're going to range over that list of documents, the 1,000. And we're going to perform that read. That's going to create that IO or put that go-routine into a waiting state. Gives the schedule an opportunity to schedule another go routine, and then we're just going to range over those items that we read to just do a little bit of work. So in this case, we're looking at about 9 or about 10, 11 lines of code for our sequential version. We're going to use the same strategy for our concurrent version than we did before. Actually, no, we're not. We're going to actually use some channels here. So we're going to use a channel here on the concurrent version, kind of change it up. So here's the find concurrent. Takes that same list of docs and a topic and the number of go routines there on line 58. In this case, what we're going to do is use that fan out bounded pattern that we talked about. So we're going to have that found variable. We're going to have our wait group. So we can wait for all of these 8 go routines to finish their read work. We're going to create that channel right there. In this case, I'm giving the channel enough space for the number of documents that we're going to be processing. Then we're going to go and create those 8 go routines. There they are. And each go routine does exactly what that sequential code did. It ranges over documents being pulled out of the channel. So it's sitting there waiting for documents out of the channel, and then it reads it, does the containment. There it is. And then right at the end, we're just going to start feeding documents into those go routines. So this is going to be our concurrent version of that find, where this time we're going to be loading documents into a channel. These 8 go routines will just pull those documents out, that fan out bounded pattern. Again, this is now IO bounded work, so that read is going to cause go routines to go into that waiting state. Why don't we take a look at what the benchmark looks like again. So let's turn off the garbage collector. Let's do that. We're going to do go test. Again, there aren't going to be any tests to run. We're going to run all those benchmarks. Let's change the bench time to 3 seconds. And in this case, again, we're going to run a single threaded Go program. So just one of my hardware threads, one operating system threads available here for you. So here's the sequential version of processing those 1,000 documents. We can see that, it's taking a lot of time there, right? We've got that 1376 number. And even though we're still on one thread, look at what the concurrent version did. It came in significantly faster. Exactly what we had talked about, right? We don't need parallelism to get that extra throughput with concurrency when it's an IO-bound workload. The context switches are helping us because it's allowing us to keep that, in this case, that hardware thread, much more busy than it otherwise would be. So we see that. Now, what happens if I decide to use all 8 of my hardware threads? Will we see any better performance? Let's look. Now, sequential shouldn't change at all, again, because I can still only use 1 out of those 8, and it hasn't. But look at the concurrent value. Notice that the concurrent algorithm is running just as fast when we used all 8 of my hardware threads as opposed to just 1. Again, there's no real extra performance by leveraging the full capacity of the machine in this case. So honestly, it's better that we run this algorithm as a single threaded Go program because it allows the other 7 hardware threads to be available to do other work. So this is again proving everything that we had talked about when we started covering OS schedulers and Go schedulers and IO bound and CPU bound workloads. When you have a CPU bound workload and you want to leverage concurrency, we really do need parallelism to get that extra performance. When it's an IO bound workload and you can leverage concurrency, we don't need parallelism. There's still a point of diminishing return on the number of Go routines that you're going to use. But you can see here how just using 8 Go routines against the 1 thread ran as fast as if we allowed those Go routines to run in parallel.